In today's session, we will see what are positive semi-definite matrices, and then we will see a new topic which is graph and adjacency matrix. But before this, there is something which I want to discuss. See, I want to discuss. I don't want to tell. I want to discuss. It means you are going to respond because it is completely for your benefit only. I want this discussion to happen. Okay, so everyone, please respond. Okay, fine. So first answer this question, that suppose let us say you have a n by n matrix. We are having an n by n matrix. Okay, and suppose we know that all eigenvalues are non-zero. What can you say about determinant of A? What can you say about determinant of A?
It is also non-zero.
Yes. So determinant of A is non-zero. So you can see that in fact this is an if and only if condition. So for an n by n matrix, you will have a zero eigenvalue only when the determinant is zero, right? So the presence of a zero eigenvalue will imply that determinant is zero. Also the determinant is zero implies that the one of the eigenvalue is zero, right? So the other statement is that at least one eigenvalue, the other way to write the same statement, at least one eigenvalue is 0 if and only if determinant of A is 0, correct? So this is the relationship between eigenvalue and determinant. Okay, fine. Now what can we say about the relation between null space of A and eigenvalue or eigenvector? It's actually about eigenvector, but yeah, let's see. What can you say about the relationship between the null space of A and eigenvectors? Is there first of all any relationship? See, what is this set null space of A? It is the set of all x in Rn such that Ax is equal to 0. So Ax is equal to 0. Can it also mean Ax is equal to 0x? Is it same as this? Does it change anything? Are they same? Ax equal to 0, is it same as Ax is equal to 0x? Yes or no? Right? So it means what? What does it mean? It means this is same as the eigenspace corresponding to which eigenvalue? Eigenspace corresponding to which eigenvalue? Tell me. Eigenspace corresponding to, I have written Ax is equal to 0x. Right? So Ax is equal to 0 is same as Ax equal to 0x. Right? So Ax is equal to 0x. So with respect to which eigenvalue is this an eigenspace? This is a collection of eigenvectors corresponding to. You still don't understand my question? If you don't understand my question, tell me. I will try to explain it in a different way. See, this, as I'm telling you, this is for your benefit. So if you don't understand my question, please ask. Yes, it's correct. Good, Shivaraman. So you have eigenspace corresponding to the eigenvalue 0. Right? See, what is an eigenspace? Do you remember? The set of all eigenvectors corresponding to a specific eigenvalue is the eigenspace. So now Ax equal to 0x is same as Ax is equal to 0x. So here 0 is your eigenvalue if it exists. Okay, if it exists. So it means what? Suppose you are asked to find the what is the null of A. Okay, so let us say you have this kind of a question. Find null of A. Okay, so this is the question. And you know that all eigenvalues are non-zero. Now tell me what is the answer for null of A. Given that all the eigenvalues are non-zero, so there is no zero eigenvalue at all. So what can be the null of A? Can there be eigenvector corresponding to zero then? No, null space is the zero space. It's just the zero vector. There is no eigenvectors corresponding to zero. So the null space is just the zero space, right? So in that case, you know that null of A is simply the zero vector. Okay. So remember eigenspace. Maybe I should write this is the same as eigenspace corresponding to eigenvector 0 union 0, because this includes 0 but eigenspace does not include 0. So here let us say union 0. Okay, fine. So now let's just recall your question from quiz 2. I guess it was a question about your left eigenvector. Okay, so there are many students who have not computed the eigenvalues. That is a different case. At least you can find the determinant. From that you can at least know whether you have a zero eigenvalue or not, or you can find the rank and find the determinant. There are many ways to actually check whether the space, what is the nullity of the space, right? No one had used the trick. Okay, you have simply found what is Ax is equal to 0 and tried to compute the x, right? See here, what is the very easy trick is that you are given matrix. Many of you, those who have found eigenvalues, at least those students could have directly written null of A is 0 because there was no zero eigenvalue. Okay, do you understand what I'm saying? I'll repeat. So there was this question, so where you had to find the left null space, right? But in that case, actually specifically it was a ah equal to a case, right? Hermitian case. So then left null space is same as the null space itself, right? So you need to find just the null space and you have no zero eigenvalue, so the null space is automatically 0. So the second part of the question, finding the null space, was something very straightforward, without which you can do without any calculation. So it is just simply 0. So do you all understand how can you answer that question without any calculation? Why the null space of that specific problem is 0? Do you all understand? Because none of the eigenvalues are 0. Is that clear? This is one thing I wanted to say. The other thing is that, if someone does not understand, please ask me. Okay, fine. The other thing is that there was this question about the algebraic multiplicity and geometric multiplicity of the inverse of B. So what are the eigenvalues of B inverse, if you know the eigenvalues of B? Do you have to calculate the eigenvalues of B inverse even though you know the eigenvalues of B? Is there not any direct relationship between the eigenvalues of B and B inverse? I have not seen anyone using the logic behind it. See, Bx is equal to lambda x. So lambda is an eigenvalue of B, right? Now let us consider B inverse Bx equal to B inverse lambda x. So it means what? X is equal to, this is identity, so you simply get x is equal to lambda B inverse x. So when rewriting, you get B inverse x is equal to 1 by lambda x. So what does this equation mean? Can you tell? What does this equation mean?
Eigenvector of B inverse is 1 by lambda.
1 by lambda is an eigenvalue corresponding to B inverse. Okay. So the what is the conclusion? The eigenvalues of B inverse are the inverses of, or reciprocal, we can say, we can simply write inverses also, inverses or reciprocal of the eigenvalues of B. Okay, so suppose let us say you have a matrix B whose eigenvalues are 1, 2, 3. Okay, so these are the eigenvalues of B. What are the eigenvalues of B inverse? Can you tell me? Tell me the eigenvalues of B inverse.
1 by 2, 1 and 1 by 2.
So you have 1, 1 by 2, 1 by 3. Okay, so these are the eigenvalues of B inverse. Suppose let us say you have a matrix with eigenvalues 0, 1, 2. Now what about the eigenvalues of B inverse? See, this is where,
0, 1, 1 by 2, right? 0, 1, 1 by 2.
see, if you have listened to whatever I have said so far, think about it and answer this question. The eigenvalues of B are 0, 1, 2. What about B inverse?
Inverse
0,
doesn't exist.
1
Yeah.
by 2.
Yes, yes.
Inverse.
Inverse does not exist, right? See, you have a 0 eigenvalue. It means the inverse does not exist. The matrix cannot be invertible. So if one of the eigenvalue is 0, the determinant is 0. It means the inverse does not exist. Okay? Remember it. Okay? So these are some important points I noticed and I wanted to tell you. Okay? And yeah, so there is one more point maybe. Fine. So let us say you have a 2 by 2 matrix. Okay? You have a sum 2 by 2 matrix A, B, C, D. You are computing its eigenvalues. Okay, so you will get a characteristic polynomial, right? So characteristic polynomial, something of this type. So once you have computed the characteristic polynomial, how will you verify whether your calculation of the characteristic polynomial is correct or not? What is P and what is Q? Can you just look at the matrix and write for 2 by 2 at least?
Yeah.
What is P?
P is trace of matrix A plus D.
Yes, so it is P is actually minus trace of A. Okay, what about Q? What about Q?
Minus multiplication of non-diagonal.
What? Sorry, minus?
Yeah, minus multiplication of non-diagonal elements. B, C.
See, Q is the determinant of A. I don't know what you said, but Q is the determinant of A. Okay, so this is how you can verify whether the characteristic polynomial you have computed is correct or not. Okay, so this is for 2 by 2. Now for 3 by 3, I thought you people know these kind of tricks to verify and all. Okay, what about a 3 by 3 matrix? So you have a characteristic polynomial of the form lambda cube plus p lambda square minus q, or sorry, plus lambda plus q lambda plus r equal to 0. What do you know about p, q and r? What do you know about p, q and r? Anyone? Anyone? No one can answer this question? At least one of the values? See, P should be just like here. P is minus trace of A. Okay. So P is minus trace of A. What about PQ? Sorry, what about Q? What about Q? Q is 1 by trace of A whole square minus trace of A square. This is not something very easy, but yeah, this is one way to check. And R is nothing but minus determinant of A. So here you need to compute A square and then do this. So this is another way to look at the coefficients. Okay, so this is 1 by 2. Sorry. Okay. I thought you people do all these shortcuts, right? So these are, see, leave about these shortcuts. But this part is really essential, which I expect all of you should know. Okay. So these are some very basic properties of eigenvalues and eigenvectors. Okay. So whatever I have explained so far, is it clear for everyone?
Yes.
Yeah. So now let's move on to week 9. Okay. In week 9, we are looking at positive semi-definite matrices. Okay. Fine. So what are positive semi-definite matrices? So positive semi-definite matrices are defined for real symmetric matrices. So we consider a real symmetric M by M matrix A, and we say it to be positive semi-definite if X transpose AX greater equal to 0 for all X in Rm. Okay, so if this condition is satisfied, then we call it to be a symmetric positive semi-definite matrix. Okay, now recall what is a covariance matrix. So covariance matrix looks like this, but maybe you have u1 minus u bar, u1 minus u bar transpose, and so you have minus u bar everywhere. So let us say we are calling this entire thing as u1, okay, or u1 dash, so which is just written as u1 in this case. So the format is anyway same. This is the format of the matrix. Okay, fine. So now you see that this is the covariance matrix for you, and this is given that it is a positive semi-definite matrix. So it means what? You take X transpose covariance matrix into X, and we have to prove that it is non-negative. Okay. Now let us see that here 1 by n is a scalar, so you can take it out, and X transpose and X are multiplied to each of this matrix. So can you see that u1 transpose is a matrix? Suppose let us say u1 is a vector, u1 is a vector in Rm, right? So it means what? It looks like this. So u1 1, u2 1, etc. um1, right? So it means how many rows you are having? M rows, right? And then here you are having u1 1, u2 1, um1, the transpose of it. So you have, this is an m cross 1 matrix, and this is an 1 cross m matrix. So the resulting is an m cross m matrix, right? So now you have n m cross m matrices, and each of this matrix you are multiplying with X transpose in the front and X in the X at the last. Okay, so this is what you are doing. And now look at this part, u X transpose u1. What is X transpose u1? Okay, so let us say X is some vector in Rm. Now X transpose means you will have something like x1, x2, xm, and your u1 is this u11, u21, um1. Now the product of this, what is the product of this? Is it a real number? Yes or no? Is it a real number?
Yes, yeah, it's one by one.
Yes. So it is a real number. Same way, you can see that if I'm writing u11, so this is what? This is x transpose u1, right? This is x transpose u1. Now what about u1 transpose x? u1 transpose x also will be the same only, right? So you will have u11, u21, um1 written here, and then here you have x1 up to xm. Now, are these two, the values are same or different? The values are same or different? Can you just see here? You see that x transpose u1 is nothing but x1 u11 plus x2 u21 plus etc. xm um1. And can you see the same here? u1 transpose x is also the same, x1 u11 plus x2 u21 plus etc. xn um1. They are the same. Can you see that they are just the same real number? Both are real numbers and they are same, right? So you see that these two are simply real numbers. So instead of writing them as some matrix product, we can just write it as x transpose u1 the whole square. Okay, so now this is a real number and it is squared. So the square of a real number is always non-negative, right? And you have sum of non-negative numbers. So this entire term becomes non-negative. So what is that we have proved? For any x in Rm, for any x in Rm, this term x transpose Cu x is non-negative. It means what? This Cu is a positive semi-definite matrix. Is that clear? Yeah.
So what is the significance of semi-definite, positive definite? What is the difference? Positive, semi-definite, and
There is nothing called semi-definite. It's positive semi-definite, or there are some matrices which are strictly positive definite, we say. So semi-definite and definite, these are some different terminologies, and sometimes we have negative semi-definite and non-negative definite. So many different terminologies are there. Everything has significance mainly because of their eigen properties of their eigenvalues. Okay, one is their structure and another main thing is their eigenvalues, which we are going to see next. Okay, fine. Okay, so the important property next we are going to see that eigenvalues of a positive semi-definite matrix are non-negative. Okay, I will write two things which we already know. From that, let me see how many of you are able to uh, give a reason why the eigenvalues are non-negative. So let us consider A, which is an n by n matrix. It is a positive semi-definite matrix we are assuming. It means what? A transpose is equal to A, fine. And then you know that x transpose AX is greater equal to 0 for all x in Rn. So this is we know. Now let AV equal to lambda V, where V is non-zero. So this means lambda is an eigenvalue of A. Now I'm telling you the hint. Use this and use this to prove the above statement. Everyone think. It is not very difficult, very straightforward only. Just think and answer me. Yeah. See, this statement that x transpose AX is non-negative, it is true for all x in Rn. So how can you use that?
so we can multiply V transpose both
Exactly.
sides.
Exactly. Good. So V transpose AV. Okay, V transpose AV is nothing but what is AV? AV is lambda V. So we have V. Let me write it properly. So you have V transpose lambda V. Now lambda is a scalar. We know that this is anyway non-negative already. Okay. So now this is lambda times V transpose V. And what is V transpose V again? Norm of V square, right? Inner product V comma V, right? So this is inner product V comma V, which is norm of V square. So you have lambda times norm V square is greater equal to 0. So this is already a non-negative term here. So what can you say about lambda then? Lambda should be,
Greater than 0.
okay. So you can see that all the eigenvalues of a positive semi-definite matrix are non-negative. Okay. And the other thing is that a symmetric matrix, take any symmetric matrix. So if you want to prove that a symmetric matrix is positive semi-definite, it is enough if you look at the eigenvalues, and if all the eigenvalues are non-negative, then you can say that the symmetric matrix is positive semi-definite. Okay. So let A be a M by M real symmetric matrix. So what do you know the properties of a symmetric matrix? So the eigenvalues are all real. You have an orthonormal set of eigenvectors, and you have this orthogonal decomposition. Right? So this kind of a decomposition is possible for a symmetric matrix. Right? So let's use this decomposition here. So X transpose AX is X transpose this decomposition times X. Now X transpose X multiply to each of these individual matrices inside will give you so exactly the same argument like we applied here. Right? So the same structure is here. So we can write this, replace it with X transpose V1 square and so on. And so you see that each of these terms are non-negative. And you know that if the eigenvalues are non-negative, then this entire term is going to be non-negative, and vice versa also. So if the entire term is non-negative, then you know that each of this lambda should be non-negative. Right? So if you have a real symmetric matrix, right, and you know that all the eigenvalues are non-negative, then X transpose AX is non-negative. Okay. So this is how you can verify whether a given symmetric matrix is positive semi-definite or not. Okay. So is it clear? If you are given a symmetric matrix, how to verify positive semi-definite? Is it clear? You simply have to find the eigenvalues and check whether they are non-negative. Okay. Fine. Shall we do a problem now based on this? Okay. So look at this question here. So is the given matrix symmetric or not? 4, 2, 2, 2. Is it symmetric or not?
Yes, ma'am, symmetric.
It is symmetric. Okay. And then it is given that f of x comma y is X transpose AX. How can we write X transpose AX? I guess there is a mistake here. It should be X transpose AY. So which statement is correct here? What is the error here? F of x comma y is X transpose. I don't know what is that they are trying to do. So this let's write it. What happened here? Let's write the statement and see, then we'll understand what should come here. Let us take xy this is xy transpose, right? So I guess the problem is with the terminology. So let's say you have maybe this let's call it some u. Okay. So what is u? U is x comma y, xy. So this is your u. Okay. U transpose means it is xy. So what is u transpose a u? So you have xy and then 4, 2, 2, 2 and then here xy. So first let's multiply this part, which is 4x plus 2y, and the other part is 2x plus 2y. And then when you multiply this further, you are getting 4x square plus 2xy plus 2xy plus 2y square. So which is 4x square plus 4xy plus 2y square. Okay, so I guess here what they wanted to write is this: f of x comma y is, or f of u is u transpose au. This is what they wanted to write, I guess. Okay, so in that way f of x comma y is this statement. So this is correct and this is incorrect. Okay, f of x comma y, where u is x comma y, is u transpose au. Fine. All right, now is it positive semi-definite or not? How will you find? How will you know that it is positive semi-definite or not?
Eigenvalues, and if they are positive,
Yes,
find
so find the eigenvalues quickly. Everyone quickly find the eigenvalues. What are the eigenvalues of this matrix? Anyone computed the answer?
3 plus minus root 5.
So what are the decimal values for it? Approximate decimal values. What is root 5? So the eigenvalues you have got is 3 plus or minus root 5. Right? These are the eigenvalues of A. So what is root 5? Approximate value 2.236, right? So 3 plus 2.236, 3 minus 2.236. Are they both non-negative?
Yes.
So it means, is it positive semi-definite?
Yes.
Okay, fine. And what is mean by negative semi-definite? If all the eigenvalues, so instead of greater equal to 0, you will have less equal to 0. And in that case, all the eigenvalues are less equal to 0. That's all. Okay, fine. So up to this, is everything clear? What is positive semi-definite matrix and how to identify a given symmetric matrix is positive semi-definite or not? Is it clear for everyone? Yeah.
Yes.
Okay, fine. Okay. So now the next thing is that you take for any matrix A. Okay, you take any m by n matrix. Okay, for any m by n matrix means what? You have a transformation T from Rn to Rm. So the corresponding matrix A is m by n. Then you see what is T star T. T star T, the domain is Rn and the codomain is also Rn. So it means you have A transpose A. So the size of A, so A transpose is n by m, right? So A transpose A is n by n. Same way, here you see that AA transpose. A is already an m by n matrix, and AA transpose should be m by m, right? So now A transpose A and AA transpose are symmetric matrices. Now we are claiming that they are positive semi-definite. So first of all, are they symmetric? Are they symmetric? What is AA transpose the whole transpose? It is A transpose whole transpose into A, right? Because AB whole transpose is B transpose A transpose. So when applying this formula here, you will get this, right? Now what is A transpose whole transpose?
A itself.
When A itself. Good. So you have again AA transpose. Similarly, can we also see that A transpose A whole transpose is again A transpose A, because it is A transpose time A transpose whole transpose, which is A transpose A, right? So both are symmetric matrices. And then for positive definiteness, for AA transpose, you need to take an X in Rm, right? And X transpose AA transpose X is, now you know that you can simply rewrite them. So it is A transpose X transpose A transpose X. Now they are vectors. So for vectors, if you have U transpose U, it is norm of U squared, right? So recall that U transpose U is norm U square. So here this is what exactly I used here also, right? So using that property, here you see that this is norm of A transpose X whole square, and this is a non-negative term. Okay, can you give a similar argument for A transpose A? For A transpose A, your X should be from which space? Yeah, for A transpose A, your X should be from which space? Here for A transpose, X is from Rm. For A transpose A, the size is given here. So what should be your X? X should be a vector from?
Rn.
Yes. Everyone, please be responsive in the class. Okay, so X in Rn. So it means you have X transpose A transpose AX, right? Which you can write as AX whole transpose AX. Again, which is norm AX square, and it is non-negative. And so you can see that A transpose A is also positive semi-definite. Okay, so these two matrices, whatever is your matrix A, you have that AA transpose and A transpose A are positive semi-definite. You don't have any conditions on A for these matrices to be positive semi-definite. Okay, fine. Now with this, can you do this problem? Now look at this matrix. Is this symmetric? Yes or no? Is this symmetric?
Yes, ma'am.
Okay, it is symmetric. So how do you check whether it is positive semi-definite or not?
By properties, we can say that because
Yeah, what is the
symmet-
property?
uh, X A transpose X.
Yes, that is one way. What is the other way? Finding the eigenvalues of A. If they are non-negative, then you know that A is positive semi-definite. Can you quickly compute the eigenvalues of A? Everyone quickly compute the eigenvalues of A.
0, 2, and 4.
0, 2, and 4. Yeah. How many of you got the same answer? Anyone else who got the same answer? 0, 2, 4. So one thing you can easily immediately check is that the sum of the eigenvalue is 6 and the sum of the diagonal entries is also 6. So one possible verification, but that is not sufficient. But yes, one cross check you can quickly do. And determinant is 0, so product is 0, right? So it seems fine. Anyone else who got the answer? Just raise your hands, those who have got this answer. Or if you want time, please let me know. Okay, Ashish has got. Chirag, good. Good. Anyone needs time to complete? Okay, if no one is responding, then let's continue. So tell me which answer is correct. So the eigenvalues are all non-negative, right? So the eigenvalues are all non-negative. So if it is non-negative, what can you conclude about A? It is symmetric and the eigenvalues are non-negative. So it is
Positive.
positive semi-definite. So these two are incorrect. What about these two options? So whatever is your given matrix A, always A transpose A and A transpose are,
Same.
they are positive semi-definite matrices, right? So because of this, A, B, and C are correct options. Clear? Yeah? Is it fine for everyone? So we are completing the topic positive semi-definite here. So the concept is clear for everyone. Any doubts in this? Okay, good. So the next topic here is graph and adjacency matrix. Okay, fine. So what are graphs? First, let's see. I guess you already know what are graphs. You have seen it in Math 1 course, I hope. So what is a graph? A graph contains two sets. So is it already covered in Math 1 or not? Just reconfirming. Graphs, have you already studied? You don't
Yeah.
remember? You have studied, right? Okay, good.
That graphs
Fine.
are not.
Sorry? Rajkumar, can you please repeat your statement? I did not hear.
Yeah, ma'am. That type of graphs, I
Some
didn't.
graphs you have read anyway, right? Okay, no worries. Fine. Okay, so a graph contains two sets. Okay, so a graph contains two sets. What are the two sets? First one is a set of vertices or nodes. Okay, so which we denote with V. Okay, so let us say there are n vertices here. And the second set is a set of edges. Okay, what are these vertices and edges? So let us see. Suppose let us say 1, 2, 3, 4. We have 4 vertices. These are 4 vertices or nodes we say. Okay, and there is a connection. Okay, so these vertices are connected. Now you see 1 and 2 are connected. 2, 3, 3, 4, 2, 4. So like this, each of these vertices are connected here. So totally, you see now the connection is called the edge. So what is an edge? Edge is this connection. So there is an edge between 1 and 2. There is an edge between 2 and 4. Right? So how many edges we see? We see 6 edges here. Right? So we see 1, 2, 3, 4, 5, and 6 edge. Right? And 4 vertices. So in all these cases, you have only 4. N is equal to 4. Okay, what are all the possible vertices is given here? 1 2 1 3 1 4 2 3 2 4 3 4. These are the only possible vertices, sorry, edges, right? So in this case, you see you have 1 2 3 4 and 5 edges, and here just 4, right? And here you have 1 2 3, here 1 2 1 and no. Okay, so these are all some examples of graphs. Okay, so now look at this. Which of the following option represent the graph G, okay, where V is 1, 2, 3, 4 and your edge set is given here. This is your edge set. So you should have a connection between 1 and 2, 1 and 3, 1 and 4, 2, 3, 3, 4. So what about the first one? You have connection for 1, 2. This is fine. 1, 3 is also there. 1, 4 is also there. 2, 3 is also there. 3, 4 is also there. So you have 1, 2, 3, 4, 5. So you have 5 and all. Let's also maybe number it so that 5 and all the 5 are here. So the first one exactly matches. What about the second one? Why second one cannot be a graph? What's wrong with the second one? How many edges do we see? 1, 2, 3, 4, 5. Here also 5 only. But why it cannot be a graph for this particular edge set E? What one is missing or what is more?
3, 4 is
So 3, 4 is missing. And in addition to that, we have this 2, 4, right? And here only 4 edges are here. Only 4 edges, so automatically this is disqualified. And what about this one? This one is again having 5 and it is missing which edge? 1, 2 is missing. Right, so this is also incorrect. Right? So for this particular set of V and E, this is the graph. Fine? Okay. So now let me just say 1, this is 2, and let us say you have 3 here and 4 here. Okay, so 1. Now what is the relationship between this graph and this graph? Can you tell? Observe it properly and tell me what is the relationship between these two graphs.
Same.
They are the same, right? Okay, they are exactly the same. Now suppose, let me say, suppose I'm having I don't know how else to take. Let me take 1, 2, 3, 4. Mm, 2 to 3 is there, and 1 to 4 is there. So now what is the relation between this graph and this graph? Yes,
It's also same, I think.
it's again same, right? The same set of vertices and same set of edges, right? So the structure, the way in which we are drawing the graph never matters as long as your vertex set and edge set are the same. The way you are drawing the graph never matters. Okay, so if your vertex set and edge set are same, the graphs are all the same. Okay, so all these graphs are exactly the same only. Okay, only the way we have drawn it or the vertices, the position of the vertices are different. That's all. Okay, so these all of them are same. Okay, fine. Okay, now what are adjacency matrices? To understand the graphs, okay, we are going to use matrix representation for graphs. So how are we going to represent graphs using matrices? Okay, so let us say you are having some graph G with vertex set V and edge set E. Suppose your vertex set is, first of all, having n vertices. Okay, if there are n vertices, then the corresponding adjacency matrix is of order n by n. Okay, and what are the ijth element? It is 1 if ij or ji is an edge, and 0 if ij is not an edge. Okay, so for example, you take this particular graph. Okay, so now where are the edges? You see an edge between 1 2 or 2 1, either way you can say it. And then you can say 1 4 or 4 1. Same way 2 4 or 4 2, and 3 4 or 4 3. So these are the edges. So you can see that, so from this you can see that a12 and a21 are 1. Same way a14 a41 is 1, a24 a42 is 1, and a34 a43 is 1, and all the remaining entries are 0. Right, because you see that aij is equal to aja is either 1 or 0, you can see that this matrix is symmetric. In fact, any adjacency matrix is symmetric and the diagonals are 0. Why the diagonals are 0? So aii is 0 because we do not allow an edge to the same vertex. So vertex is a singular of vertices. So it means we do not allow self loops. So sometimes it is called self loops. Right? So suppose let us say you are having something like this. So this is not allowed. So 1 to 1 you cannot directly put an edge. Edge can be between different vertices only. That's why all the diagonal entries are 0. Okay. So what is an adjacency matrix, and why it is symmetric, and why the diagonal entries are 0? All the points are clear to everyone? I want to at least know whether you understood or not. Give me a thumbs up if you have understood.
Yes, ma'am.
Others? Very few students still not. There are many who are not responding. Okay. Okay, fine. So before doing this, can you quickly give the maybe some yeah, let's say maybe this matrix itself, this set of vertices itself, can you write what is the matrix? Can you tell me the matrix for this adjacency matrix? What is the first entry? So for writing the adjacency matrix, always write the name for the columns and rows so that it's easier. One entry is, first we know that the diagonals are 0 for any adjacent matrix, so you can fill the diagonals to be 0. Now tell me what about 1 2?
1,
1 3 is,
1 and 1, 4 is also 1.
yeah. What about 2 3?
1,
2 4?
0,
Okay. What about 3 4?
1.
Okay. Now you know this part. So it is a symmetric matrix, so you can easily fill. So it is 0 1 1, and then it is 1 0 1 0. So 1 0 1 0, and then 1 1 0 1 1 1 0 1. We have completed the matrix. So this is the adjacency matrix for this particular graph. Okay. So finding the adjacency matrix is clear, I hope. Okay. Now, what are paths in a graph? Okay, path means the way in which you can move from one vertex to other vertex. Okay, so for example, what is the path from 1 to 6? For example, how can you go from 1 to 6? Maybe you can go 1 4 3 and 6, or you can go 1 2 8 and 6, or you can go 1 4 7 5 and then 6, right? So the way in which you can move from one vertex to other vertex is a path, right? So now the question is, in how many ways can you go from, for example, here the vertex 4 to vertex 8 in less than or equal to 5 steps? Okay, so for example, here you can see that one way to go from 4 to 8 is that 4, 4 to 1 to 2 and then to 8. 4, 1 to 8. And then if you want to go through maybe 3, then how can we go? 4, 3, 6 and 8. Right? So the steps you see, it is less than 5 only. So you have only 3 steps. Right? And then maybe if I want to go through 7, then it is 4, 7, 5, 6 and then 8. So here we have 4 steps. So like this, the question is how many ways? So instead of just looking at the graph and counting, is there any other way to count the number of ways in which you can move from the vertex 4 to vertex 8? Okay, so for this, these two results will help us. What are the results? Suppose G is a graph with adjacency matrix A. The ijth entry of A par K is the number of paths from vertex I to vertex J in K steps. Okay, so the statement, read it carefully. I'll give 2 minutes. Just read it. Then we will see an example. What is the ijth entry of A par K representing? Number of paths from vertex I to vertex J in K steps. Okay, it means what? So let us say you have this graph and you have this adjacency matrix C. Now this is your A square. Okay, now this is your A11 and A11 is 2. It means what? Now read this statement again. It is the number of paths from vertex I to vertex J into K steps. So there are 2 paths. Okay, 2 paths. So use the number of paths from vertex I to vertex J in K steps. What is your K here? Can you tell me? What is your K here? What is the power of A?
2.
2.
Yeah. So it means you have 2 paths from 1 to 1
In 2 steps.
of size 2. Oh, yeah, in 2 steps. Or so the same words, let me write in 2 steps. Yeah. Can you just look at the graph and tell me what are the 2 paths from 1 to 1? 1, 2, 1. 1, 4, 1. Correct? 1 to 1, 1, 4, 1 to 4, and then back to 1. Right? Only these two are the paths of step or of step size 2. Right? So you have only 2 paths satisfying this condition. Same way you can see the explanation for each. So for example, here you see that suppose you are considering A12. A12 is 1. It means what? Only one path from 1 to 2 in 2 steps. So what is that one path from 1 to 2? Which is having 2 steps. How can you approach 2 in 2 steps? From 1 to 2 in 2 steps.
1, 4, 2.
Yes.
1 to
1, 4, 2. Now what about this 0 entry here? Why A? What is this entry? A 3, 4. Why A 3, 4 is 0? It means what? No path from 3 to 4 in 2 steps. Right? So 3 to 4, there is no possibility to go from 3 to 4 in 2 steps. That's clear, right? Yeah. So how do these entries can tell the number of paths between any 2 vertices? Is it clear? Yes?
just
Okay. So there is one more result which says that suppose if you want less than or equal to k, then you have to add all the entries of a plus a square plus etc. a par k. So the ijth entry of a plus a square plus etc. a power k is the number of paths from vertex I to vertex j in less than or equal to k steps. So you are considering all possible steps whose size is less than or equal to k. So we are adding up all these matrices a square, a power k, etc. and their ijth entry gives this answer. Okay, clear? So here is another example. So you have the matrix 1, 2, 3, 4. This is your matrix A. So you see this is A square and this is A cube, right? So here you see that in A square, you see that all the diagonal entries are 2. It means what? You take any vertex, you can go from that vertex to the same vertex again in 2 steps in 2 different ways. So what are those 2 ways? So 1 to 2, 2 to 1, 1 to 4, 4 to 1. So like this you can do for any vertex, right? 3 to 4, 4 to 3, 3 to 2, 2 to 3, right? So you see that you have 2 different parts of size 2 or step size 2, right? Now if you look at a cube, what does a cube tell you? A cube tells that so all the diagonals now are 0. It means what? You cannot have a path from 3 to 3 or 1 to 1 or 2 to 2 or from any vertex with step size 3, right? So if you are moving 3 steps, then you are at some other vertex. You cannot be back at 3 in 3 steps. Okay, that's why all these entries are 0. So you understand the meaning of each point of a square, a cube or any power of a, right? Okay, fine. Now let's move to the spectrum or eigenvalues of a graph. The eigenvalues or spectrum of a graph or the eigenvalues of its adjacency matrix A. Okay, so the eigenvalues or the spectrum of the graph G are the eigenvalues of its adjacency matrix A, right? So A is symmetric, spectrum is real, right? So here it means what? If you have a symmetric matrix, you already know all the eigenvalues are real, right? And you have an orthonormal basis of eigenvectors. So you know that adjacency matrices are symmetric and you have only real eigenvalues. Okay, so here are some examples. So these are some adjacency matrices, their corresponding eigenvalues and eigenvectors. Okay, fine.
So
Oh,
the spectrum, I'm hearing the terminology spectrum for the first time. Is it same
spectrum.
as eigenvalues for a
Yes,
spectrum
spectrum.
pertains to a graph, right? It's not for matrix. Since we are using graph here, the word spectrum is used. Am I right? Or
See, this is actually widely used in many places. Spectrum for operators. So mainly in operators, we use what is the see. There is a very famous topic in mathematics itself, which is called the spectral theory, and the spectral theory is for any general operators, right? So this spectrum is not restricted. The terminology is not restricted for graphs alone. It is applicable for operators also. But in this course, we are mainly using this word spectrum to refer to all the eigenvalues of adjacency matrix. Okay, so spectrum here refers to the set of all eigenvalues. Okay,
thank you.
fine. Okay. Okay, what is a bipartite graph? A graph G is equal to V comma E is said to be bipartite if V can be partitioned on into V1 and V2 such that all edges are between V1 and V2. What does that mean? So it means let us say you are having a vertex set like this. You have a vertex set 1 2 3 4. Okay, now suppose I'm having 1 2 3 4 and these are my edges. Okay, so my edges are 1 3 1 4 and 2 3. Can you tell me what is my V1 and V2? What is V1 and what is V2? So V1 is a set where there is no edges between them. So you see 1, 2, 3, 4, right? So between 1 and 2 there is no edge, between 3 and 4 there is no edge, and all the edges are between 1 and 2, v1 and v2. So either from 1 to 3 or 1 to 4 or 2 to 3 and 2 to 4. So you see that this is a bipartite graph. So this is your v1, this is your v2. So are you able to understand what are bipartite graphs? If you are able to partition your vertex set into two parts such that there is no edge between the partition inside the partition, but only between the partitions. Okay, so that is called a bipartite graph. Okay, so vertices can be renumbered in any order to get that type of structure of a bipartite graph. Okay, so for a bipartite graph, you the adjacency matrix can have this type of a structure. Okay, so but is it always that given a bipartite graph you will always have this type of structure? Sometimes what is that need to be done? You have to renumber the vertices so that you get this structure. Okay, immediately you may not be able to see this structure, but once you just renumber them, then you will be able to see. Okay, for example, let us consider this graph. Some different color I wanted to pick for graphs. Okay, so let us say you have 1, 2, 3, 4, 5, 6. Okay, so the graph is given in this way. Okay, now is this a bipartite graph? Yes or no?
Yes.
Yes, right? You see the top 3 forms one set and the bottom 3 forms one set. But suppose the numbers are given like this: 1, 2, 3, 4, 5, 6. Now, what is the adjacency matrix? Can you tell me? Of course, the diagonal entries are 0. So you have 0, 1, 0, 1, 1, 3 is 0, right? And then again 0, 1. And then for 2, you have 1, 0, 0, 0, 1, 0. 0, 0, 0, 1, 0, 1. Just check whether I am writing correctly. And then for 4, I have 1, 0, 1, and then 0, 0, 0. Then 0, 1, 0, 0, 0, 1, and then 0, not 0, 1, 0, 1, 0, 1, 0. So this is the adjacency matrix. You see, this is bipartite. This is bipartite, right? But this structure is not there. So how to get this structure? So we will get this structure if we choose this in the first and then this in the second part. So it means what? We need to renumber them. So it means what? Now the same graph, so we just have to renumber them. So it means what? So let's renumber it like this: 1, 2, 3, 4, 5, 6. Okay. So now you can check that this graph, the adjacency matrix will look like this. So between 1, 2, 3, there is no edge. So what will happen? So here you have, this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So between 1, 2, 3, there is no link. So it means here all the entries are 0, 0, 0. Right? And then you have links here only. Please check whether I am doing it correctly. 1, 0, 1. Okay. And then here you have 1, 0, 1. Symmetric matrix, right? 1, 1, 0, 1, 1, 1. And these entries are 0 because within 4, 5, 6 there are no links. So now we got the other above structure. So this is your matrix B. This is your matrix B. And this is your B transpose. Can you see that? Yeah. So this is your B. And this is B transpose. Yeah. Fine. Okay. So the graphs, the adjacency matrix of bipartite graph, we can have this structure provided you have given the correct numbers for the vertices. Is that clear? Yeah. Okay. So for paths in bipartite graph, there are some special properties. For example, path from I to I. So it is possible that you can go from I to I only in even number of steps. Why? Because from I, you can go back to I. So for example, 1 to 5 and then 5 to 1 in even step. Or you can do 1 to 4 and then 4 to 3, 3 to 6, 6 to 1. So in 4 steps you can go. So either in 2 steps or 4 steps, like that only you can go. You cannot go in odd number of steps. Not possible for odd number of steps. What does that mean? All diagonal entries, or in general, you can say that all the diagonal entries of A power k where k is odd are all 0. Okay. So it means what? A power k I is 0 for all k odd. It means including A, all the diagonal entries for any A power k is 0. Okay. So if you have this property, then you can say that the graph is bipartite. Okay. So do you all understand what is this property? If all the diagonal entries are 0 for all the odd powers of a matrix, then the graph is bipartite. Okay. Why is that? Because you cannot have odd number of steps from the same entry to same entry because of the structure of a bipartite graph. Okay. Is that clear? Okay. So the next thing is, what can we say about the spectrum of a bipartite graph? What is mean by spectrum again? Eigenvalues, right? So if lambda is an eigenvalue of a bipartite graph, then minus lambda is also an eigenvalue. Okay, so once you know one eigenvalue, you know the other eigenvalue. Okay, so let us say you have a vertex set of n vertices. So let's say you have this partition. So this is your V1 and this is your V2. Okay. Now, if lambda is an eigenvalue with eigenvector V, where this is your first S components and this is your the remaining components. So this, let's call this first S components as U1 and the remaining components as U2. Now AV is equal to lambda V. Okay, and you have this particular matrix representation for A. Now let's write the V in terms of U1, U2. Okay, so now you see that when you multiply 0 times of u1 plus b times of u2, so simply bu2 and then b transpose u1 plus 0. So you have bu2 b transpose u1, which is equal to lambda u1 u2, right? Because this is your av and this is lambda v. So this is simplified form of av you have. Now you consider this. Instead of u2, you now consider minus u2 here. Now you see that this is 0 plus minus BU2. So the first term become minus BU2 and then you have B transpose U1 plus 0. Right? So now what is that you can see? What is minus BU2? BU2 from here you can see that BU2 is equal to lambda U1 and B transpose U1 is equal to lambda U2. From here this you can see. So let us apply it here. BU2 is lambda U1. So minus BU2 is minus lambda U1. And B transpose U1 is lambda U2. So we can take the lambda commonly, and this is what you have. Now you can take the minus outside so that you have minus lambda U1 minus U2. So now this is your, maybe let's call this as W. So what is that you have got? AW is equal to minus lambda W. So it means lambda minus lambda is also an eigenvalue. So if lambda is an eigenvalue, minus lambda is also an eigenvalue. Okay? Can you all understand that if lambda is an eigenvalue, minus lambda is also an eigenvalue? Is it clear? Yes or no? Yeah? I don't see any response. I don't know where is this going. Okay, fine. Now, how to find if a graph is bipartite? Of course, this is the property we are going to use to check whether a given graph is bipartite. So, for any non-zero eigenvalue lambda, minus lambda is also an eigenvalue, then the graph is bipartite. Okay, what is the proof of this? So, let us say lambda and minus lambda are eigenvalues. With this assumption, consider A power k. What do we know about the A power k? So if all the diagonal entries of A power k is 0 for k odd, you know that the matrix, the graph is bipartite. So we are going to use that. Now for A power k, so this is something which I talked about in the beginning. So I told you if lambda 1, lambda 2 are the eigenvalues of A, then lambda power k, lambda 2 power k, etc. lambda n power k are the eigenvalues of A power k. In the beginning, I told a specific case of this where k is equal to minus 1. Right? Okay. So now for odd, so these are the eigenvalues of A power k. Now when k is odd, we already know that lambda 1 power k plus etc. Lambda n power k is equal to 0. Why is that so? Why is that so? What is the reason for this statement? Can anyone tell the reason for this statement? What is it? What is that we know? A power k I equal to 0 for all I when k is odd. Right? Now, what is this meaning? This means that trace of A power k is 0. But what is trace of A power k in terms of the eigenvalues?
Sum of all eigenvalues.
Yes. So it means you want lambda 1 power k plus etc. lambda n power k is 0. So that is why here you have lambda 1 power k plus etc. lambda n power k equal to 0. Okay. So it means what? You have trace of A power k is equal to 0. Now also you can see that some of the, yeah, this is what I have written the explanation here. So it means what? There is no path from I to I of odd length. So it means what? We have proved that it is a bipartite graph. Okay. So to prove that some graph is bipartite, what is that you need to do? You just have to look at the eigenvalues. So for every non-zero eigenvalue lambda, if you have minus lambda also as an eigenvalue, then the graph is bipartite. This is how you can check bipartite graphs. Okay. Fine. So here is an example. So you have two matrices here, which are representing two different graphs. So for this graph, you can obviously see that it cannot be bipartite because you cannot partition the vertex set. And also from the eigenvalues also you can see that for 3, minus 3 is not an eigenvalue. So minus 3 not an eigenvalue. So it means what? It is not bipartite. And here you see, apart from the, for all non-zero eigenvalues, these are the non-zero eigenvalues, the negative is also present. So it means what? This is bipartite. Okay, this is bipartite. Now how can, from here can you see it is bipartite or not? The structure, what is the partition? Can anyone think and tell what is v1 and v2?
1, 3 and 2, 4. Yeah.
Exactly. So 1 3 2 4 if you take, so 1 to 2, 1 to 4 you have and then you have 3 to 4 and 3 to 2. So these are the vertices and edges, and v1 and v2 are the partitions. Okay, so you have a bipartite graph with these as the eigenvalues. Okay, so
These right, these are all kind of looking simple matrix. And I was watching the video. Professor was showing getting these eigenvalues and vector by inspection. Is there any easy way you can teach us? I mean, he was following some easy way to get this
okay,
eigenvalue.
I guess he has used circulant matrices, I guess, because this is a circulant matrix. That is what he has used, I guess. I don't remember what exactly professor has done, but you can notice that this is a circulant matrix, yes or no?
Yeah, this is a circle.
Yes. So this is a circulant matrix. That is one thing. So from circulant matrices, you can for circulant matrices, how to find eigenvalues and eigenvectors, you have some specific formula, right? So you can use that. That is one thing. And always one apart from circulant matrix also, if you take any matrix where all the row sums are exactly same, what can you say? See, this is some observation which is true for any matrix, not necessary for circular matrix. Suppose let us say you have a matrix A such that all row sum are same. So it means what? So suppose A is equal to A11, A12, etc., A1n, A21, A22, etc., A2n, and then A1, AN1, AN2, etc., ANN. Now summation j is equal to 1 to n, aij is equal to alpha for all I. Okay, 1 less equal to I less equal to n. If this is there, what can you say? So in this particular case, what is your alpha?
2.
2, right? So in that case, what can you say? Yeah. So you can say that here, whatever matrix you are having times 111, what does it give you? So vector with all the entries 111, all the entries 1 vector. So when you are multiplying this vector to A, what is that you are getting?
Yeah, 4. Some of
This is like n by 1 matrix, you can say. You have, for this I'm writing, so you have summation j is equal to 1 to n a1j, summation j equal to 1 to n a2j, and so on. Is that correct? When you multiply, this is what you will get, yes or no?
Yes.
Right, it means what? You are getting alpha, alpha, alpha. So it means you are getting alpha times of 1 1 1. Yeah.
mhm.
So it means what? Whenever you have a matrix where all the row sums are same, that is an eigenvalue, and the corresponding eigenvector is 111. This you can say without calculation. So here you can see that for this matrix 2 is an eigenvalue with eigenvector 111. That you can say without any computation. Okay, because of the property that each row sum here is 2. Each row sum is 2. Because of that, you can very easily see that the eigenvector is 111 with eigenvalue 2. Okay.
Yeah, mentioned, yeah, sum of the first row, the eigenvalue. Then he was also writing other eigenvectors. Next eigenvector 1 0 minus 1 0
Yes, that
also.
is completely based on the circulant matrix properties. So this
Okay.
is a circulant matrix. Maybe if you want, I have to write what is the circulant matrix vectors here. So let me do this. So after this session, I will write the circulant matrix properties here, and how we
Okay.
are obtaining it. I will add it and then upload this PDF to you.
Yeah,
Okay.
yeah.
Ma'am,
I think in the next session, I think 10th week,
Yes.
there's a session for circle and matrix, like Fourier basis.
Okay, so
Right.
maybe I can do it at that time also. But
Yeah.
anyway, here also I will add it.
I was
You can
curious
refer it.
to know because it may be useful in the exam, so we
Definitely,
don't need to do all
definitely.
the work to get the
Yes, yes.
eigenvalue. That's what I was curious to know
Sure,
whether
I
it's
will
easy
add it.
way.
Yeah, yeah.
Thank you.
Okay. And
Ma'am,
this, yes,
ma'am, if the matrix is 5 by 5 and three of the eigenvalues are zero, and the other two are means negative of each other, then the graph is also bipartite, or
yes, it is bipartite. Okay, it is still bipartite. Apart from the zero eigenvalues, if the non-zero eigenvalues are negative of each other are there, then it is still bipartite only. Okay. So from that, whatever you said, what can you say about the bipartite adjacency matrices of bipartite graphs with odd number of vertices? Suppose you have a bipartite graph where the number of vertices are odd. What can you say about the adjacency matrix?
So there will be 1 0.
Yes, one of the eigenvalue is definitely zero. Okay, so this is one observation you can see. Okay, so is it clear? Yeah.
yes,
So, what are the topics we have seen today? What is a positive semi-definite matrix, right? And how positive the eigenvalues are positive semi-definite matrix or non-negative, right? So that is the first important thing we saw today. And with this property that the eigenvalues are non-negative, so given a symmetric matrix, you find the eigenvalues. From that, you can identify whether it is positive semi-definite or not. And then we saw what are graphs. For graphs you have a vertex set and edge set, and with this edge set you can form an adjacency matrix, and this adjacency matrix is always symmetric with diagonal entries 0. Okay, and then we saw the parts of a matrix can be found by looking at the values of the a par k matrix. Okay, and the eigenvalues are referred to spectrum for a graph. And what is a bipartite graph we saw? If we are able to partition the vertex set as two different sets where there are no edges between the sets and all the edges are between v1 and v2, then we call it to be a bipartite graph. So you have edges only between the sets and not within the sets. Okay, and for bipartite graph you have this kind of a matrix structure. Okay, and then you can see that for bipartite graph the diagonal entries are all 0 for any odd powers of the matrix. Okay, and you for other important property about bipartite graph is that if lambda is an eigenvalue, then minus lambda is also an eigenvalue. So sometimes this property is referred to as the spectrum is symmetric about the origin, they say. Okay, the spectrum is symmetric about 0, not origin, 0. So it is symmetric about 0. So if one is there at a distance lambda from 0, the other should be also at a lambda from the 0 in the other side. So it is symmetric about the value 0. Okay, fine. So these are the topics we have seen today. I hope it is clear for everyone. We will continue again on Tuesday. Okay, fine. Okay then. Thank you.
Thank you.
ma'am,
Yes.
I have a question in the quadratic form.
Okay.
Yeah.
What is
If
your